Okay, so today we really start the first chapter of this class. Last time, chapter 0 was a live overview of everything, the whole class, even some complementary chapter. But today we will go to a regular speed, I hope, for the chapter 1, and this is first part of chapter 1, chapter 1a. So if you are some people on YouTube finding this video by pure coincidence, and you want to know more, so you can go this video. There is some slides on these two websites. So this is a website in Montreal. This is a site here in India in the Institute of Mathematical Science. So if you go on this website, then you will see this video book, The Art of Bijection Matrix. So now we are in part 4, and there will be, so this is chapter 0 last time, and if you go inside, then there is the full detail of the video, and in front of each item, in each section, there is a number which is a number page for the slide. You can get the slide on this website, and here you have a number which is the time on the video. If you click on it, then you go directly in the video on the YouTube or in the video in Math Science. I cannot put the direct link on. In YouTube, you can put the direct link by giving the time up to 1 second. So today we will start from an elementary point of view. We'll start with 4 examples of orthogonal polynomial. It will be the Chebyshev first and second kind, and we'll work with the Hermite polynomial and the Laguerre polynomial for alpha equals 0, no parameter. And I will prove directly they are orthogonal without knowing nothing of the general theory. So I will not work with Motzkin path or this weighted path. I will work directly with this polynomial. And we start with Chebyshev polynomial, first kind. So this comes from the trigonometry. If you expand sinus n plus 1 theta for any n, it's going to be up to sinus theta, a polynomial un in cosine theta. And this polynomial has been introduced by Chebyshev, and they are called Chebyshev polynomial second kind. There is 2 kinds of Chebyshev polynomial. So Chebyshev, if you see, there is a French, the English way to translate the Russian letter. So sometimes people work like this, or they write in French like this, or like this, even in English like this. Maybe the best is to write in Russian. Chebyshev, and this is the first name, and in fact here is Chebyshev. And so if you look this stamp, maybe you think that this man was very, very old, from 1821 to 1946. So in fact, he was born in 1821 and died in 1874. So maybe this was time for issue of the birthday, 100 year and something for Chebyshev. Well, I would let you make the computation. And so this polynomial, Chebyshev un, it's a sequence of polynomial. Each polynomial is of degree n, and in fact they are orthogonal polynomial. So if I take orthogonal in the sense of classical analysis, it means that for this integral, with this measure, this is a scalar product of 2 polynomials, and this will be 0 if m is different of n, and it will be, if m equal n, then this will be non-zero. It will be pi over 2. This is a Kronecker symbol. So this is the classical definition of a sequence of orthogonal polynomial. It's orthogonal polynomial on the real number. Each polynomial is of degree n. The integral of product is 0 if m equals different of n, and the integral for m equal n is non-zero. Even here it's a positive number. So now we are going to give a combinatorial interpretation of this Chebyshev polynomial as a matching of a certain graph, matching polynomial of the segment graph. So I denote by Sn of x the matching polynomial of the segment graph, what it means. So the segment graph is a graph with endpoints. The edges are in I and I plus 1 are connected by an edge. It's this segment graph. And a matching, what is a matching? It's a choice of edges in red, which must be 2 by 2 disjoint. No edges has a common vertex. So you take all possible matching. So if you write this number A and K, the number of possible matching of the segment is better. Instead of taking 1 to n, I will take 0 to n minus 1. So it is a segment of n integer. So the number of matching having k dimers. Here 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is a segment of length 10 and k equal 2. So take the number of such matching, and the matching polynomial is going to be this polynomial, the sum over all possible k. So there's a minus or plus, minus 1 power k, this coefficient a and k, and x power n minus 2k. So by definition, this is the matching polynomial. So if there is no dimers, if the set of dimers is no dimer, means then this term is going to be x power n. So this is a polynomial of degree n. The coefficient of the term of biggest degree is 1. So this is called a monic polynomial. This is defined polynomial. And then the relationship between Chebyshev second kind and matching polynomial is very simple. You replace x by 2x. So it's almost the same, but it's a matching polynomial. It's monic polynomial. The Chebyshev polynomial, the coefficient of biggest degree is going to be 2 power n for the Chebyshev second kind. So I can also write the same way like this, that the matching polynomial is the sum over alpha over all possible matching of the segment 0 and minus 1, minus 1 the number of dimers, which in all these curves, all along the chapter I will denote forever. Between 2 bar means the number of elements, so the number of dimers, and x power n minus 2, the number of dimers. So what does it mean? You see, this is a typical configuration. You take a matching, and you put some weight everywhere. You put a weight minus 1 for dimers, a weight x for a point having no dimers, which means I call this isolated point in the graph. So we are going to sum over all possible choice of dimers. The weight of this is the product of all the weights. So it will be minus 1 to the square, product of the x power 5. So this is the interpretation up to a factor 2 of the Chebyshev polynomial of the sinus. It's a sum of the weight of all this kind of configuration you can also write this like this. Sigma over all possible matching, minus 1 the number of dimers, x power I p of alpha means the number of isolated points of the matching. I p of alpha, the number. So I will, maybe, I don't know if it's a good notation, but we will use this in many other chapters. Number of isolated points of the matching alpha. So this gives you a combinatorial interpretation of the first most simple orthogonal polynomial, the Chebyshev second kind. So Chebyshev, this polynomial, are strongly related to Fibonacci. So Fibonacci is much earlier, the 12th century. So what is the relation between Chebyshev and Fibonacci? There is a so-called Fibonacci polynomial. Fibonacci polynomial are like this. They are defined by Fn of x. It's almost it's very similar, but you put minus 1 the number of possible of dimers, A and K again, but you put an x for each dimers. So this Fibonacci polynomial is sigma over all possible matching of minus x power the number of dimers. So if you follow the class part 1, we use this, the Fibonacci, for many things, for counting dig paths with the bounded height, etc., etc. It was better, more convenient to use this polynomial instead of the Sn, what I call the Sn. The S is for segment, the matching of the segment graph. And this polynomial satisfies this Fibonacci polynomial, this three-term recurrent solution. And why is it called Fibonacci polynomial? Because if you take the sum of all the coefficients, the total number of matching satisfy this very classical recurrent solution for the Fibonacci numbers. It is three-term recurrent solution, Fibonacci numbers, and you extend this three-term recurrent solution with the variable x. How to prove this? If you take any matching, then you have two different choices. Maybe this point is isolated. There is no dimers on this point. So this gives you Fn plus 1 equal Fn, this term. And if there is an x, if there is a dimer, which is weighted minus x, this gives you this term. So it's very easy to see from the Fibonacci polynomial to show that they satisfy this three-term recurrent solution. Just by looking what happened on the last point, there's two different choices which correspond to these two different terms here. Yes. Yes. If you replace x by minus 1, then this will be weight 1, and Fn of 1 is the total, the sum of all the absolute value of the coefficient, which is the Fibonacci number. So it is the Fibonacci. And then what is the relationship with the segment S of x, which was the matching polynomial of the segment, which was the Chebyshev second kind. So in fact, they are just, if you take the reciprocal of this Sn, I recall it's a matching polynomial of the segment graph. So if you take the reciprocal, what it means taking the reciprocal, it means you replace x by 1 over x, and you multiply by x power n to get again a polynomial. And so taking the reciprocal of this polynomial, which is the sum of all the weight of all this, so you have to take 1 over x, means you are going to put an x everywhere here, and keep the minus 1. So going from this picture, this interpretation to this one means taking the reciprocal. And I can write this as a Fibonacci polynomial when I replace x by x2. If you replace here, you see, replace x by x2, and replacing everywhere x by 1 over x, and multiply by x power n, this gives you this picture. So Fibonacci, segment, matching of segment graph, reciprocal is the Fn of x2. Because the diamonds is in this is count for x to the square. Here a diamonds count only for x. And so if I look the Chebyshev second kind, they satisfy this three-term recurrent solution with this initial term, three-term recurrent solution. The Fibonacci polynomial, they satisfy an analogous three-term recurrent solution. This I will not prove, it's just consequence, elementary consequence of trigonometry with sinus. But from this three-term recurrent solution, from the three-term recurrent solution of the Fibonacci polynomial, from this three-term recurrent solution Fibonacci, from the relation reciprocal polynomial and Fibonacci, then you can easily deduce this relation that the Chebyshev is equal to the matching Sn replacing x by 2x. So I claim that I have a commutative interpretation of this orthogonal polynomial, this simple orthogonal polynomial, Chebyshev second kind, by giving the matching diamonds on the segment. Analogous, not exactly the same, but analogous three-term recurrent solution. Because if you look the matching polynomial of the segment graph, analogous to the three-term recurrent solution of the Fibonacci, or the Fibonacci number, they satisfy very easily this three-term recurrent solution. If you look such matching with the weight x for isolated point, -1 for diamonds, then the sum of the weight of all this is equal to Sn plus 1 of x is equal to, so again, the same similar way. If the point is isolated, then you get this term. If the point is not isolated point, means there is a diamond on it, weighted -1, this gives you this term. So this is a proof that of the relationship between Chebyshev UN and matching of the segment. Of course, with the initial condition, they have the same initial condition. So when I was a kid in college, we have to learn about what is cosine, sinus 5 theta, sinus 3 theta, sinus 4 theta, all these trigonometric formula. Now you can impress your kids very easily. Okay, take, you want to compute this? Sinus 5 theta? Okay, take a segment of length 4, take all possible diamonds. You take, so this is the matching, the Sn, the matching polynomial of this segment graph. Here you have x4, you have 3 terms for x2, here you have 1 term, and then you replace x by 2x, and x is cosine theta. So you have this term, this term, this term, and then you get an expression of sinus in terms of this Chebyshev in terms of cosine theta. So trigonometry becomes very easy. Just putting diamonds on the segment in different way, and you get all possible. You can take sinus 10 theta, etc., etc. I don't know if Chebyshev was doing this, but at least now we can, in elementary school, we can teach trigonometry this way, in a visual way, by putting diamonds on the segment. First exercise, what are the coefficients of this matching of the segment graph. We have seen in this picture there was 1, -3, +1, but in general, what are the coefficients? There is a very simple explicit formula. So prove that the number of ways to put k dimers on a segment of length n is exactly this binomial coefficient. So this is an expression of explicit expression of the matching polynomial of the segment graph. You sum over all possible k. K is the number of dimers you are going to put in the segment. So -1 power k, or -1 for each dimers. Number of ways, a and k. And the x power is the number of isolated points, which is x minus 2k. Now you can read this coefficient on what is called in the Western countries the Pascal triangle. So this is a Pascal triangle, written in he was writing things like this. This is a Pascal triangle, the binomial coefficient, n choose k. So I suppose everybody knows the binomial coefficient. I will not make too much speech about binomial coefficient. So now you look this in diagonal, 1, 3, 1, 1, 4, 3, etc. You see that this is exactly all these coefficients in diagonal. This is the binomial coefficient n minus k choose k. So this is the coefficient of the matching of the segment graph. So this is the coefficient of the Chebyshev polynomial. And we have seen sinus 5 theta, it was 1, 3, 1, the coefficient. So if you sum all these coefficients, you get 1, 2, 3, 5, 8. You get the Fibonacci numbers. This is well known. The Fibonacci numbers appear also in the diagonal like this of the so-called Pascal triangle. I say so-called Pascal triangle because in China it was known much before. The Pascal, or even in Persia, and it was known also, and in India. Pingala was much earlier. It was 2,000 years ago, more than 2,000 years ago. So Pingala has some binomial coefficient, and he was related to the grammar of the Sanskrit, where there is some short syllabus and long syllabus, lagu and guru. So there was a lot of study about this, because there is a certain number, the measure matra, and there is some short matra, long matra. This is a long matra, and this is a short matra. So sequence of this. So Pingala probably was aware not only of the binomial coefficient, but of the Fibonacci numbers. And I think I look, thanks to Amri, show me a historical paper, and I see the Fibonacci number F index 5, or maybe not all of them, but the Fibonacci numbers was implicit in this Pingala writing. So this is very old, all this, maybe much earlier in the Babylonian time, or I don't know, maybe in India 5,000 years ago, with Rishi teaching, maybe. So it's part of the heritage of humanity for a very long time. So a second example. You cannot, okay, this was Chebyshev second kind. Why second kind? Because there is a Chebyshev first kind. Chebyshev's first kind is cosine of n theta equal Tn of cosine n theta. Chebyshev first kind can be defined by this. Again, the same way, the same integral, but there is a slight difference. This is a two-term reconciliation. And now I claim that the commutative interpretation of Chebyshev first kind is going to be the matching polynomial of the circle graph, or the cycle. So you take a cycle with endpoints. The graph is edges, you see all the green edges, and you put some dimers again, choose some edges of two consecutive points, such that the edges are 2 by 2 disjoint. So we have seen that Chebyshev is related to Fibonacci. So who is the analog of Fibonacci for Chebyshev first kind? The analog is Luca. There is some Luca polynomial, Luca numbers, and this is exactly the analog of the Fibonacci polynomial. So let's start with the matching polynomial of the cycle graph. I call this the cycle graph of length n. And again, you define the very same way. Cn of x, C for cycle, it's a polynomial. The sum over all possible matching of the cycle graph, minus 1, the number of dimers, x power, the number of isolated points. And we are going to see the relationship between this polynomial and Chebyshev first kind, Tn of x. And I claim that Tn of x, the Chebyshev polynomial first kind, is half of the matching polynomial of the cycle graph when you replace x by 2x. To prove this, you have to show that they satisfy the same kind of same three-term recurrence relation. So I will not give the three-term, yes, already gave the three-term recurrence relation for Tn, which come from trigonometry. I will not give a proof. Let's go back to classical geometry. But I claim that the Cn, the matching polynomial of the cycle graph, satisfies this three-term recurrence relation with again x. But before, for the Fibonacci, it was 1 here. But now it's not exactly explicitly 1. It's lambda 1 equal 2, and lambda n equal 1 for all other integer n. So it's always 1, except lambda 1 equal 2. With a starting point, C0 equal 1, C1 equal x. So there is a very slight difference with the other kind of Chebyshev. It's for the matching polynomial segment, you have lambda 1 equal 1. For the matching of the cycle, you have this recurrence relation. And I leave you with an exercise. First exercise, or second exercise. Give a proof, check that matching polynomial of the cycle graph satisfies this three-term recurrence relation. So now what is analog of Fibonacci polynomial? This is a Luca polynomial. Instead of putting an x for each isolated point, I'm going to put an x for each dimers. In fact, a minus x. So Luca polynomial is the sum of all possible matching of minus x power. This is a number of edges of the matching. For example, here, for the cycle of S4, the Luca polynomial is 1 minus 4x, 4 possible ways to put an edge, minus 2x2, there is 2 possible ways to put 2 edges. When the graph is totally covered by edges, this is called in graph theory the perfect matching. There is no isolated point. So the perfect matching is a constant term of all this matching polynomial. Now if I take the reciprocal again, I replace x by reciprocal of ln of x2, because I'm going to replace x by x2 to have a dimers is going to be x squared, because there is 2 points. Taking the reciprocal of this, if I take the reciprocal, Cn ln of x2, then I get this relation. That's the reciprocal of the Cn is the Luca polynomial for x2. And I get the Cn, the matching polynomial. This is the cycle graph in another notation. Gamma n, the cycle graph of length n. And then this is a relationship, again, analog to the Chebyshev second kind, the Tn of x is half of the Cn of 2x. Again, we can do trigonometry. We can do in a very easy way. For example, this is the Luca polynomial for the cycle of 4. I replace x by x2. It gives this polynomial. I take the reciprocal. I get this polynomial, which is going to be the kind of the cycle matching polynomial of the graph. So the cycle polynomial, if I replace x by 2x, and I get this, which is cosine of 4 theta. So you can do easily trigonometry. Maybe there is something wrong here. Yes. Here I replace it's C4 of 2x, and then I take half of this to get Tn T4 of the Chebyshev first kind. This is T4 of cosine theta. Take this, reciprocal, replace x by x2, take the reciprocal, then replace x by 2x to get, and then taking half of this gives you Tn. So again, you can ask, what is the explicit formula for this matching polynomial cycle? Explicit formula for this coefficient here, Chebyshev first kind. So exercise, maybe a little not so easy. The first one is easy. This is medium. Do the first one for the coefficient of the Fibonacci or the matching polynomial segment. Then there's a nice formula. Now it's you have to prove that n times this is equal to n minus k times this. Don't work with a rational fraction. Put integer on both sides, and you have to prove it, and maybe it's better prove it bijectively. Not doing recurrence relation, trying to do a lot of calculus. We are in a bijective course, so you are supposed to know calculus and easy calculus. So also the first exercise to prove that the coefficient of the Fibonacci was binomial n minus k choose k. This is easy to see bijectively. So do this bijectively and you get the coefficient. So I can write that the matching polynomial of the cycle is this nice polynomial. Okay. There is some comments? Yes. No? Okay. Because when there is question or comments, video is not recorded. So maybe I will repeat, if there is question, I will repeat the question. And, for the video, you can even, from the studio, you can get the camera on the student, but no sound. So maybe I will repeat, but if there is no way to repeat the comment. Okay. So we have seen matching polynomial of two graphs, segment graph, cycle graph. So we can ask, well, what are the other possible graphs? Infinite family of graphs which depend on an integer n, and maybe they will also give other orthogonal polynomials. So first definition for a general graph, like this, definition of the matching polynomial of the graph. So you get a graph, it's a non-oriented graph with edges, single edges. And a matching is just a choice of edges, 2 by 2 disjoint, they have no common vertex. So matching is a set of 2 by 2 disjoint edges. And when I put a weight on this matching, by putting a minus weight for each edges and an x for each isolated point. And in a very similar way as the first two examples of segment and cycle, I get the definition. The matching polynomial of a graph is sigma over all possible matching, minus 1, the number of elements of the matching, the number of edges in red, and x power the number of isolated points of the matching, which can also rewrite like this: sigma of minus 1 number of edges x power n minus twice the number of edges if n is the number of vertices of the graph. So you get a polynomial of degree n if n is the size, the number of vertices of the graph. Coefficient of x power n is 1, so it's a monic polynomial. And let's think about some infinite family of graphs defined for every n and see what happens of the matching polynomial. So the most simple, maybe the complete graph. Every vertex is connected by an edge. Usually in graph theory, this is denoted by Kn. And matching polynomial of this, we are going to see that this is exactly the Hermite polynomial. In fact, there is different Hermite. There is a physics Hermite, probabilistic Hermite, combinatoric Hermite. This is the probabilistic Hermite. There is slight variation, but between the Hermite. So we will show combinatorially that this is orthogonal polynomial. Now the Laguerre polynomial are exactly the matching polynomial of the bipartite graph, complete bipartite graph KNN. This is KNN. You put n point on the top level, n point here, and every vertex on the top is connected by an edge by a vertex below. So if you take the complete this graph with n vertices, I claim that this is a very classical Laguerre polynomial. Usually in the chapter 0, I show you the Laguerre index alpha. There is a parameter in the alpha, but here alpha equals 0. In the special case alpha equals 0, you get this Laguerre polynomial. So I am going to show that this polynomial, in a certain way, are orthogonal polynomial for a certain sequence. I am not going to show the measures, the integral. We cannot do this, we don't know how to do this combinatorially, but we know how to do the moments of the polynomial and give interpretation. So first, Hermite polynomial. So in chapter 0, you have seen the last time the Hermite polynomial defined by an integral with a certain weight measure here, the measure and integral from infinite integral. This is 0 for n different of m, and this is square root of pi n factorial for n equal m. So there are many possible definitions of the Hermite. There is this orthogonality, there is a exponential generating function, there is differential equation, there is sometimes people call the Roderick formula, also defines the Hermite polynomial. Maybe if I have time in chapter 5, we will give a proof of this. So this is, in this story, this is the so-called physicist Hermite. We will do exponential generating function in chapter 5. We'll explain what it means. So this is a physicist Hermite, but the probabilist Hermite, usually they denote probabilist Hermite polynomial by H with an E. Sometimes people put a tilde. So the only difference, you see, it's in the exponential generating function. And we will use this Hermite combinatorial interpretation. So between the physics Hermite and the probabilist Hermite or combinatorial Hermite, there is this. Of course, you can go from one to another very easily. So if you read classical book on Hermite polynomial, you will see this definition here. But here, in this all the course, even the course of part 1, part 2, part 3, the last classes, I use this definition. And not to be embarrassed with this notation for many classes. In this course and all the previous course, what I denote by a chain of x was in fact this Hermite polynomial. So don't be confused with this one and this one. Now all along the class, this means the probabilistic or combinatoric Hermite polynomial. So Hermite polynomial, I can define it. I claim that I can define it the combinatorial Hermite, I can define it exactly as a matching polynomial of the complete graph. So here is the matching of the complete graph. And definition, so I will take this as a definition. I will not use integral coming from measure. I will take this definition. The Hermite Hn of x is a matching polynomial of the complete graph. And I'm going to give a proof that these polynomials are orthogonal for something. So I will prove this, they are orthogonal for a certain, I will not have the measure, but for something in a formal way. So again, IP of alpha is a number of isolated points. So in fact, the matching of the complete graph, if you prefer permutation, symmetry group, augmentation, if you prefer group theory, then it's also in bijection with Hermite configuration. Hermite configuration is you take the symmetry group denoted by sigma n, you take a permutation written like this, and in involution, in the symmetry group is a permutation which is equal to the inverse. In other words, if you take the square of the permutation, this is the identity. You see here, 1 go to 10, and 10 go to 1. And you have fixed points like 4 go to 4 in blue. I have written the fixed point, sigma y equal I, and in non-black it's a pair. So you see an involution can be written like this. Involution has some fixed point and some cycle of length 2. This is the same, this is in bijection with the matching of the complete graph. Each isolated point is going to be weighted x, and each cycle of length 2, which corresponds to an edge, is weighted -1. So we call this sometimes Hermite configuration, because there will be Laguerre configuration, Charlier configuration, Dexter configuration, Jacobi configuration. There will be many in the hierarchy of orthogonal polynomial. Each will be interpreted by some finite object of configuration. Here we are in a very simple case of the four first orthogonal polynomial, Chebyshev first, second kind, Hermite and Laguerre for alpha equals 0. And so if I can rewrite this Hermite polynomial in the following way. If I call d of sigma of the permutation the number of cycles of length 2, if I call fix of x the number of fixed points of the permutation, so I can rewrite the Hermite. Instead of matching of the complete graph, I can rewrite it as a sum of the weight over all involution. So it's a sum over all involution permutation of -1 then d of sigma. D is the number of cycles of length 2. D is for dimers. In physics, monomer, dimers. And x is the number of fixed points. So see, for this configuration here, I have x power 5 minus 1 power 3. So you sum over all possible such configuration, and you get this polynomial I defined by Hn of x. So this is the combinatorial Hermite, and we will see in the chapter working on orthogonal polynomial and exponential structure, we will see that this Hermite configuration, we get immediately the generating function. So this will be a consequence in chapter 5. We will prove this, that generating function of this gives you this interpretation. See, inside the x is this, so -1 is this, t2 over factorial 2, and taking the exponential in taking this. So if you follow the class number 1, part 1, you understand this, but I will suppose you have not followed part 1, and I will recall all this exponential principle in chapter 5. There is a strong relationship at this level between orthogonality and exponential structure. And this were for the Hermite, for the Laguerre, for the Jacobi, for Charlier. And this was a big confusion at the beginning of the coital theory of orthogonal polynomial, because at the beginning, the interpretation of the coefficient was with exponential function. Interpretation of the moment of measure are also very close. For example, for the Hermite, we are going to see the moments are involution of fixed point. So on both sides, I talk of a certain duality between the polynomial and the moments, the orthogonality. And on both sides, at the lower level of the ASCII table, they are almost the same coital object. And so the confusion was working with exponential structure, but without understanding really what means the coital expression of orthogonality. Everything was confused at the lower level. And slowly, it was really two different theories: interpretation of the coefficient of the polynomial and interpretation of the orthogonality, the moment, and etc. So it's at the upper level, this is totally different. At the bottom level, everything is almost confused and the same. So now, even if you don't know anything about generating function, you just know elementary combinatorics, you can exercise, you can prove this. You have to show that what is the number of matching of a complete graph, or what is the number of involution having a certain number of fixed points. So this will be an exercise. It's just counting elementary combinatorics. You have to know what is the binomial coefficient, and choose k. The number way to choose k element over n element, which is n factorial divided by k factorial, factorial minus k. So if you just know elementary combinatorics, you must be able to do this exercise. And second exercise, give a proof that this matching polynomial of a graph, this Hermite polynomial, that satisfy this three-term. This is a general three-term relation for orthogonal polynomial. So the Hermite Hn satisfies this relation with bk equals 0 and lambda k equals k. Oh, you have recurrence relation between the take the complete graph, delete the point, and then what happens? For Fibonacci, it was very easy. Now you have a complete graph, so there's a little more work to do. So I claim that chapter 1, I introduced 4 elementary orthogonal polynomial, Chebyshev first, second kind, Hermite. Now it's time to introduce Laguerre polynomial. So Laguerre polynomial, I will denote it by ln of x. It's a special case of the general Laguerre. In this class, I will introduce this Laguerre with parameter alpha, but for the first chapter first, elementary level, alpha with 0, and I don't have any parameter. And I will introduce ln of x. It's not exactly the same as the Laguerre of the classical Laguerre. In fact, there is an n factorial factor and a minus 1 power n, but it's almost the same. So for me, the Laguerre polynomial here, ln of x, will be exactly the matching polynomial of the complete bipartite graph. K and n, for example, this is a possible matching of the complete bipartite graph. In fact, you can also see this matching as an injection. You take n element, and you have an injection from this n element to the same set of n elements. This is an injection. From 6 elements, the segment 1 to 6, to the segment 1 to 6. Again, exercise, elementary combinatorics. What is the number way to choose a matching of the complete bipartite graph? Okay, this gives me this formula for the Laguerre polynomial. This is the coefficient here. For the number of matching. In fact, this is a number of matching with k isolated points. So try to give a proof of this. Elementary proof, just with binomial coefficient, choosing, you have to choose a subset, choosing a permutation, and factorial, it's a number of permutation on an element. This is number of ways to choose k element over n. So if you just know this, then you must be able to do this exercise. So what I denote ln of x, in fact, in the usual Laguerre in the literature will be this Laguerre I am taking multiplied by minus 1 power n divided by n factorial. If you open Wikipedia, everything, you will see, in fact, this polynomial. It came from the classical measure of the... But combinatorially, I will take this polynomial. Because it's going to be monic polynomial. Again, the Laguerre polynomial will be monic polynomial in power n. The coefficient of x, biggest degree will be x power n, and the coefficient will be 1. Now again, so we have an explicit formula for this Laguerre. If I take the definition of the matching of the bipartite graph, now again, there is a three-term recurrent solution for this matching polynomial and satisfy the bk equal to k plus 1 and lambda k equal k to the square. So the size shows that this Laguerre defined as a matching polynomial of the bipartite graph satisfies this recurrent solution. So we have four families of polynomials, which are four possible matching of graphs. I have four families of graphs. Taking the matching of each of these graphs, I have a three-term recurrent solution. I have explicit formula for the coefficient. I claim they're orthogonal. But what means orthogonal? So now the main definition is the definition of formal orthogonal polynomial in a formal way. So classically, in analysis, polynomials are on a real number, sometimes even the complex number, and the orthogonality is related to the scalar product of two polynomials, where d mu is a certain measure on the real number. The integral maybe is finite, maybe is infinite. And this measure maybe depends on a function which maybe have a jump, or maybe it's increasing, there is a positivity increasing the function, there is a Stieltjes integral, there is sometimes people call it continuous orthogonal polynomial or discrete orthogonal polynomial. But all this we will forget. We will not work on the real number, not on the complex number, but we will work on the polynomial on any ring. On a ring, sometimes you need to divide, so I will take a field. But I am going to define formally what is the orthogonality. So this scalar product, in fact, is defined. There is a function f. The function f, in fact, if I apply it to x power n, this gives me this definition. So f of xn are called the moments. In the classical theory of orthogonal polynomials, they are called the moments of the orthogonal polynomial. And there is a very famous problem in analysis. If you know the sequence of moments, the mu n, how to find the measure of the orthogonality. Sometimes the measure is unique. If the lambda k are all real number positive, strictly positive, but sometimes this is a hamburger problem, they are not unique. So maybe there is no... To find a combinatorial interpretation is some people, because when I showed it to seminar with physicists, where is the measure? You don't... for me, I work only with the moment, mu n. Where is the measure? You don't find the integral, the measure, the positivity, etc. But for me, no, I have no positive number. I have just a formal polynomial. And so also the confusion is that if you take the measure for the Hermite polynomial, then it's going to be exponential of t2 to the 2. So inside the function appearing here will be the same, the exponential of the moment, the exponential for the coefficient. So there is an exponential function everywhere. So it seems that everything is confused. So, but for the combinatorial level, we will work only with the mu n. So if you take any sequence of mu n, then you can define orthogonality. If you give me the mu n, then this defines me a linear form. F will be a linear form of the space of polynomial. So what are the space of polynomial? So I take any ring k. So k can be real number, complex number, if you have some parameter. Like the Laguerre depend on the parameter alpha. Maybe there will be 2 parameters, alpha, beta, or maybe 4 parameters. So I will have polynomial in one variable x, and k maybe with the ring of polynomial in the formal in the parameter. But for me, all alpha, beta will be formal variable. And at the end, maybe, okay, I will put alpha equal 1 over 2, or alpha positive, or alpha in q, etc. But during all the process, this will be formal letters, formal variable, which are different from the x. This is a variable for the polynomial. This will be polynomial in the formal parameter, so maybe q, usually it will be integer or q rational number, or anything you want. So I will take a sequence of polynomial in one variable. This polynomial will be polynomial on the ring of polynomial with coefficient in k, and definition. So a sequence of polynomial in k will be called orthogonal. So sometimes it's called formal orthogonality. In fact, in the Chiara book, I was inspired by Chiara book because he takes polynomial on the real number, but he defined f. He defined it like this, with no integral, nothing, with a linear form on the space of polynomial with real coefficient. But it works very well for polynomial with any coefficient in a ring K. So definition, they will be orthogonal if and only if there exists a linear form, a linear functional, you know, elementary linear algebra, f of the sum, okay, a linear form of the space of orthogonal polynomial, satisfying the 3 following conditions. Condition 1, degree of Pn equal n for every n. We start with n equals 0, p takes 0. Condition 2, the f of pkpl is 0 for k different of n. This is the orthogonality, it's a scalar product. F of pq is a scalar product. This must be 0 as soon as the 2 indices. And third condition, if k equal L, this must be non-zero. So maybe I should say that the ring is a domain. If the product of 2 elements is 0, then each of the elements is 0. But this is important condition when you are on real number. This must be non-zero. Okay. When it is positive, if what is it? Not automatically, no. You need 3. Because we will work, we will give some proof, commutative proof, and we will work with some polynomials such that this is always 0. So we will see. It's no more orthogonal. No, it's very important that it's not 0. Positivity. Yeah, okay. Yeah. If the measure is positive, yes, it's not 0. Yes. But here I am working in a formal way, so I have to state condition 3. So you can ask, for example, we have seen Chebyshev polynomial first and second kind. So for the first kind, the moment are mu for if its index is even, is a binomial coefficient 2 and 2n. If n is even, 2n plus 1 is 0. This is Chebyshev first kind. Very simple moment. In fact, this is not exactly the moment. This is a modified. This is a moment of the matching polynomial of the segment of the cycle. So there is a slight modification. It's not exactly the Chebyshev, but the modified Chebyshev. I mean the matching of the segment, the matching of the cycle. They are orthogonal polynomial with this kind of moment. And I will prove this in a purely commutative way. So moment, you see, it's 2n to n, and here the Catalan number. This is very classical, well-known number in combinatorics. 1 over n plus 1, 2n to n. And I will give a proof of this in chapter 1. Direct proof. This is maybe not adapt the proof I'm going to give to this polynomial. So this is the combinatorial way with matching of segment, matching of cycle. If you go back to the definition of Chebyshev, then the moment there will be a factor 1 over 4 power n, the moment of Chebyshev. So it's not exactly the same. But combinatorially, when I work with I change the variable, I get this. Now I claim that the moment of Hermite polynomial, for this formal definition, in fact, we will see in the general theory that the sequence of moment is unique. If you have orthogonal polynomial, moment of the sequence of moment is unique up to multiplying everybody up to a factor. And if you have a sequence of moment, there is at most one sequence of orthogonal polynomial for this sequence up to a multiplicative factor. So moment of the Hermite we have defined here as a matching of the complete graph is going to be then this, which is a number of involution with no fixed point. By the way, you can, I forget to say, but exercise shows that the number of involution with no fixed point is equal to this product. Easy exercise. Easy. Moment of Laguerre polynomial is n factorial. Is permutation. In this course, I am going to give a proof that the moment of the Hermite are given by this. A combinatorial proof. So defining the Hermite as the matching of the complete graph, I have to show that it satisfies the three conditions of the formal definition of orthogonality, where the moment, the f, the linear functional f, is defined by the action of f on the monomial, which is this.
These are the perfect matching.
Yes, this is perfect matching. So there was what I was saying before. There was some confusion. So Hermite polynomial is interpreted the polynomial by number of matching, and the moment is perfect matching. But in fact, when you go up on the classification of orthogonal, you see that this is totally, completely different. Interpretation of coefficient, you use exponential structure of the spaces, all this theory of Montreal, etc. I have explained in part 1. I will explain chapter 5. This is exponential way to structure too. But now this perfect matching is totally interpretation of orthogonality moment will be totally different. At the lower level, they coincide, so maybe some confusion. Also, the moment of the Laguerre n factorial, and we have seen the Laguerre polynomial as a matching of the bipartite, which is injection from n to n. So it's close to a permutation. It's a local quasi-permutation. So again, at the lower level of the classification of orthogonal polynomial, there is some similarity on both sides, but this is totally two different theories. So there was a lot of commutative model for exponential geometric function and polynomial. But there is another commutative model for moments, which we will see in chapter 2. This is the weighted Motzkin path and all this story, starting with François, Flageolet, and the speaker. So this is typical pedagogical example. In this class, in this course, all along the course, there will be a lot of sign reversing involution. Some involution with pair to by they are killing one term is killed by another one, and this replaces the classical what is called the inclusion-exclusion principle. So the modern way to see inclusion-exclusion is to construct sign reversing involution. And the orthogonality of the Hermite is going to be a first simple example of such construction. So this is very pedagogical. This is the first step to understand the sign reversing involution. So to do this, we have to show that f is a linear functional defined by the moment, which is a number with involution with no fixed point. F of pkpl equals 0 if k is different of l. So inside the f of product of polynomial, you have the two polynomials, which are interpreted. The f is interpreted by something, so you have to combine the two interpretations, the polynomials themselves and the moments, and the combination of the two is you have to give a commutative interpretation of what is called the linearization coefficient. And I will do this linearization coefficient for the Amid polynomial. So what means linearization coefficient? So there's an easy lemma. Okay, so any sequence of orthogonal polynomials are a basis of the space of polynomial. And so if you take the product or any of these polynomials k for any k and l, then this may be expressed as a sum over all possible polynomials. This is a finite sum. And here there is a coefficient which depends on k, l, and n. This is called the linearization coefficient. And the lemma, what is the lemma? The lemma gives an expression for this coefficient when the pk are a sequence of orthogonal polynomial for a certain linear functional f. The lemma says that this coefficient is the f of a product of three orthogonal polynomials of the pk, pl, pn divided by f of pn to the square. So you guess the proof. The proof is in one line. You take this equality. I should put f sigma over I of pi. You multiply by pn. But don't put the same n. Take the summation over I, over all I. Multiply everything by pn and apply f. Because of the orthogonality, so you get here f of pk, pn, pl. And here you will get this coefficient multiplied by f of pi, pn. And if I is not equal to n, it's 0. What remains is I equal n, which is this. So in the classical analysis theory, people are very interested in the linearization coefficient to compute this f of product of 3. But in combinatorics, we can do much more. We can compute the f of the product of any numbers of polynomials. And what I'm going to do is to give an interpretation of f of this. Starting from Hermite as a matching polynomial of the complete graph, starting with f defined by the moment number of involution with no fixed point, which is the perfect matching on the complete graph. So the perfect matching on the complete graph exists if the number of elements is even. So we have all the ingredients, and now I will give the proof. Matching, so this is only what I need. Definition of the matching, and definition of f. F is defined by this, and from this definition, I am going to prove the following proposition. Proposition f of the product of any Hermite polynomial with index n1, n2, and k is going to be explicitly equal to the number of perfect matching of the graph, the sum of all these graphs, kn1, kn2, kn2, I mean this, you see, I take a complete graph with n1 vertices, a complete graph with n2 vertices, a complete graph. So this graph is inside each of the, this is a complete graph, and any vertex of this can be connected to any vertex of this. This definition, this notation means, I don't know if it's standard notation, that the edges of this graph, maybe the picture is not good, it's you can connect any two vertices inside one of these bubbles here, And you can connect any vertices between one of this graph and one of this graph. So all here they are complete, each component. And then you can connect any graph, any vertex here with any vertex here. So this is the definition of this sum of all of this complete graph. And then the condition is there is no internal edges. The condition, the number perfect matching of this graph with no internal edges. No internal edges. So this is an internal edge, you see. Here there is no internal edges. In this graph, this is a complete, perfect matching of the graph, but I don't have any internal edges in each of these blocks of this complete graph Kn1, Kn2, Kn3, etc. So I claim this proposition. This is exactly number perfect matching of this graph with this condition. Knowing so Hermite polynomial is a matching polynomial of the complete graph, and f applied to polynomial is defined by f over x power n equal the number of perfect matching of the complete graph on 2n elements. Before proving this, there is immediate corollary, the orthogonality. F of Hn is n factorial Kronecker symbol. You must have a perfect matching of this graph with no internal edges. So the only way is to connect 1 point here, 1 point here. It must be perfect. So the number of vertices here must be equal to this one. If it's not equal, there is no way to find such perfect matching with no internal edges. So this is a Kronecker symbol. Even I can give you the coefficient here. If n equal m, what is the number of ways to connect this and this? This is n factorial. So now I give a proof of the proposition, which is more general than to give the orthogonality. In fact, you get completely the linearization with as many Hermite polynomial you want. So first step, take the product of all these Hermite polynomials. So it's going to be each Hermite is a matching of a complete graph. So the product is something like this. You see, the product is you are going to in each of the complete graph take a matching minus 1 the number of minus 1 number of diamonds, number of edges, x power total number of isolated points. So the underlying chromatal picture is this. I have all this complete graph, and the product of the Hermite is something like this. For each Hermite, you choose a matching of the complete graph. Maybe not a perfect matching, but here is a possible choice of edges in each component, n1, n2, n3. And now I have to put x power, the number of isolated points. So here are all the possible isolated points. So I put the weight, minus 1 for each edges, x for each isolated point. And now you have to take, with this interpretation, you have to take the f of the product. F of the product, knowing that the f is going to work on the isolated point. You have a certain number of isolated points, and f of x power this is a number of involution with no fixed point, the moment, on this set of isolated points. So you have to put a perfect matching on all these blue points, on all these points with an x. So f of this is going to be this summation. So you get a pair alpha 1, alpha 2, alpha k, a matching in each of the complete graph, plus another matching, which is in the sum of all these complete graph, and which I call this graph here. Once you have defined each matching, What remains is an isolated point. What remains, I take only the isolated point in each of the one you have chosen, alpha 1, alpha 2, okay? There is some isolated point, so I can construct the complete graph of this, and I will take a perfect matching of this. So you are taking the complete graph. This graph is a complete graph. The vertices are the set of isolated points you get once you get the choice of alpha 1, alpha 2, alpha k. So it's good to have a visualization of this. This is the visualization. See f of this product of Hermite. In red, minus 1, 1, I have the choice for each complete graph of matching, which gives me the Hermite. What remains is x, and taking the f of this, f is acting only on the x power the number of this isolated point. The blue point, the linear form is acting on this monomial x power the total number of such isolated points, and on this isolated point I put a perfect matching, which is, I claim that this is going to be the moment. So this is a picture. You have some edges in red, some edges in blue. And this is typical of what we are going to do. We have to define an involution, a sign reversing involution, which is going to kill all this 2 by 2. I mean, to a certain, you have here a configuration. And I can associate another configuration, which is this one. These blue edges. I put in blue, see, I have red edges. In blue is the edges coming from the F. And in blue, there is edges which are internal, inside. Or there is some edges outside. So take these edges, one of these edges, put it in red. This gives you another configuration. And now if this edge is red, there is a weight minus 1. So these two configurations are going to cancel. When I are counting them, there is one configuration and this one, another configuration with which the number of minus 1 has chance parity. So the idea, this is the most simple idea for involution in this class. I am going to pair this configuration with red edges and blue edges. You have to join them 2 by 2. So which means I am going to define an involution phi, which means to each configuration like this, you define another configuration. For example, like this, you have to give a precise definition, such that the weight, one is the number of minus has change parity. They are going to cancel 2 by 2. And because if this involution means, okay, I have this, suppose your involution tells you, so you have a certain process. We say, okay, I have this configuration, my involution phi will tell me, okay, these edges become red. If I apply again phi, this edge is red this edge is red is becoming back blue. So you have to define the definition of the involution, but the involution is not defined. You cannot define this involution on this, because there is no red edges, there is no blue edges. So everybody is going to cancel 2 by 2, and except certain configuration, which are exactly the one I want to show in the theorem, that the f of the product of Hermite is going to be exactly the number of such configuration. So this is really the typical example of a sign reversing involution. So now people killing involution, they kill 2 by 2, but in this violent word, it's maybe not appropriate to call killing involution, no, sign reversing involution. And so if you want really to define the process, if you have a configuration, you have to say, okay, if there is some edges inside which are blue or red, you have to say, okay, which one you choose to flip red from blue. So there is different choice. For example, okay, I am going to all possible internal edges of all possible graphs. I will make a total order on these edges. And then if there exist some edges which are blue or red inside, then I will take the minimal, the total order which are minimum, and I will change the blue in red or red in blue. And if I apply again the map phi, what is the minimum in the order? It will be the same. So this is a possibility, to put a total order on the internal edges, blue or red, take the minimum and make the flip. And if there is no internal edges, blue or red, then you cannot do anything. So the involution phi does not work. But where it works, everybody is paired 2 by 2, and everybody cancel, and what remains is exactly once you have killed all this internal is this. And this gives the proof. So see, we are typically on there will be many in this class, many such. What is the question? I'm not consecutive.
Which one should I flip? I mean, if you give me.
You gave me take a total order on the internal edges of all the graph, independent of the color. Okay, so take the minimum in this total order. If it's blue, you change it in red. If it's red, you change it in blue. Because when you change the color, again apply phi. Give me the minimum in the. But the minimum, if it's blue or red, it doesn't depend on the color. So if you apply phi twice, it will be back to the identity. And so I gave a proof, in particular, the proof of the orthogonality.
But you are taking as a input that f of x power n is given by perfect match.
Yes.
You don't derive that.
I have to define f. The moment Hermite polynomial is defined as a matching polynomial of the complete graph. Now f is defined as f of the monomial, the moment. I define f like this. For all the f of the monomial x power n is a number of perfect matching or involution with no fixed point on a set of n elements. So n must be even. So this is the definition of f. And I claim that I have given a proof that this polynomial defined as matching polynomial of complete graph, they are orthogonal in a formal way for the definition to the f defined by moment, number of involution with no fixed point. We will see later that, in fact, the moment, if they are orthogonal, then the f is unique up to a multiplicative factor. And sometimes some of my colleagues say, but this is not completely beautiful proof because you have to choose something, you have to say, okay, total order, there is different way to define the involution, and sometimes you don't need really the involution, you just need the idea. So I will finish this class with this idea. Another thing, I am going to give a variation of this proof, but without explicit construction of the involution. So suppose you take a f, capital F, is a certain set of internal edges. Right, so it's a certain set of internal edges, and I'm going to take a partial sum. You take in the big summation, you have to do f of the product of Hermite. I take a partial sum, so I fix the matching alpha 1, alpha 2, alpha k. And there is a matching alpha of the, so this is the edges in red, this is the edges in blue. But I fix such that all this, the edges are in red of this matching, plus union the edges in blue, all these edges blue or red are going to be in the fixed set capital F. For example, here they will be capital, they will be these edges, these 3 edges, and these 2 edges. So in this big summation, I am interested only in the term having this fixed subset F. So the total number of terms in the summation will be 2 power F, the choice of the color or one of these internal edges. And so it is very easy to see that this summation is 1 plus minus 1. Sigma for all edges 1 plus minus 1, which is 0. The 0 is behind my face, behind this picture. So this is 0, you can believe me. Okay, and this gives a proof. Another proof, maybe is more beautiful, I don't know. With you limit, you see, to where you can apply the involution, but you don't need to say which one to put a total order. So for purist bijective man, you can people you can do this. But for me, everybody know I don't like inclusion principle, and this is better because sometimes if you have some weight, we will apply this in the course to define the involution, and then there will be weight on the everything alpha, beta, because orthogonal polynomials there are going to be a lot of weight. So if the involution is weight preserving, then you get also the proof. Because when you do inclusion exclusion, is with the weight, it's beginning to be something a little. So I will finish with the example of Laguerre polynomial. So for the Laguerre, it's very similar. Laguerre is the matching. If you start with the definition of the matching polynomial of this complete bipartite graph, to prove that the mu n and n factorial, there is a proposition that f of the product of Laguerre is a number of perfect matching of the graph K. So analog in an analog way, you see, I take this direct sum, means in each component K, N1, N1, etc., there is a complete bipartite graph. And then the sum of this means you can connect any vertices at the top level in one of this bipartite graph can be connected to another vertices below in one of this block. And then I claim, so internal edges mean you are inside one of these blocks, and the f of this is a total number of perfect matching with no internal edges. And so exercise, so yes, proposition is an exercise. Apply, just make the very similar involution from Hermite. You can do this by yourself for the Laguerre. And as a corollary, if you have f of ln, only 2, then it's 0 if m is not equal to n, and if m equal n, the Kronecker symbol, then you can prove that this is n factorial to the square. So this is typically, this proof, you see, is typical of the proof we will see in this class. And next time, I'm going to stop here. Next time we will do analog proof for the Chebyshev polynomial second kind. So the involution is going to be a little more, maybe subtle and more instructive, because this involution is going to be exactly the model for all possible, many other involutions. There's 5 different theorems in the class with weighted paths, and this will get inspiration from the involution I'm going to give you for the Chebyshev second kind. The Chebyshev second kind is the matching polynomial of the segment graph. The moments are going to be Catalan number. It's a dig path. So one way I have the matching, I have the segment graph. On the other way I have the path. And when I will have put weight on all this, then I will get the very powerful involution, which will go in many chapters. There will be 5 theorems in the class, which are all inspired by this. And what I'm going to do with the Catalan path and the Chebyshev polynomial. Okay, so thank you very much. Thank you.